mentioned this here in the last meeting. I've mentioned this in the last meeting, right? If you're doing factorization, the first thing that you need to do is pull out an HCF, then check how many terms we have in the expression, because the number of terms in the expression will dictate which approach you use. And so the key word that you need to remember here is terms, plural form. And so what this means is, if you looked at this carefully, terms can only exist if you have a plus or a minus sign. And this is why when we're dealing with an exponential expression that has a plus or minus sign, we are using factorization. Factorization is just a tool. It's a tool that enables us to do one of the two things primary purpose of maths, or one of the two primary purposes of maths, which is simplify. It's a tool. It's a simplification tool. And so this is why if factorization is so heavily dependent on the number of terms, plural form, that they are in an expression, it implies that, remember, terms are separated by a plus or minus sign. And so there has to be a plus or minus sign in order for there to be a term, in order for them to be many terms in the expression. And so this is why we're using factorization as a simplification technique when we have an exponential, expression that has a plus or minus sign in it. And so here, more often than not, you're going to use HCF. In fact, most of the time, right? And so here, if you look at it carefully, you can see this here. See this, and this here. If I factor this out of the bracket, pull it out, then I'm left with this in the bracket, and then that will cancel. Right? So if I have to put it like this here, it's like this here, saying A times B. So this is A, that is B, minus C, that has to be A. It's the same. So I have to give it the same variable, times C. See, these are different, so I can't give it the same variable, over A multiplied by B. That's the same as that. And so what we're doing here now is we're taking out an HCF. So we A into B minus C over A times B. A and A will cancel. So you'll have to B minus C over B. Same story. It's the exact same story here. We're going to do the exact same thing. So if I take it out, it'll be 2 to the power 2n into 2 squared minus 2 to the power 1 over 2 to the power 2n. 2 to the power 2n and 2 to the power 2n will cancel. Here again, if you're looking at it carefully, this is what? A fraction. If it's a fraction, then the denominator cannot be 0. And watch how brilliant this is. Right, check here. 4 to the power n plus 1. What dictates the shape of a function? It's a and b, isn't it? And so a is greater than 0, b is greater than 1. So we have an increasing function that lies where? Above the asymptote. There's no q value here. So therefore, the asymptote is the x-axis. Can you see that? So the function will do exactly this. Is there any values that are negative? No, there's not. Or any values that are 0? No, there's not. And so therefore, it'll always lie above the x-axis. Therefore, this will always be greater than 0 and not equal to 0. So there's no imaginable n value that I can input here that will make 4 to the power n plus 1 0. Sorry, 0. So this here will be true for all values of n. So there's no restriction. So I don't need to mention any restriction at the end here. That's the power of it. Multiplied by 2 to the power 2. And 2 to the power 2 minus 2 is 4 minus 2, which is 4 minus 2 is 2 over 4, which is half. And that's how we solve that. All right, guys, I hope you're starting to think. These are all, see this here. What's this? A function. What's this? A function. What's this? A function. And so I can do it like this here. A function minus a function over a function, or I can say a function over a function. You'll see this a lot. Trust me, you're going to see this a lot. Right. So yeah, this is why I was able to. Can you see, just by sketching, if you fasted sketching, you can reason quick in maths. That's why you understand functions, you understand maths. I keep saying it. Right, so now you can see a side-by-side analysis here. If you do a side-by-side, you can see. See, the only thing that's different between these two here, between exponential expressions with multiplication and division, and exponential expressions with plus and minuses, is the last step. It's the last step. Here we used exponential rules to simplify, but see what we used here, factorization, right here. We use factorization. Right, can you see that? Yeah. Okay, guys. Yeah. Okay, so we got that done, right? Let's look at the next question. Okay, yeah. So that's about it. That's literally about it. Now let's talk about factorization. Um, see, factorization. Can you see? There's so less explanation here because we're using the exact same ideas. We're using the exact same ideas. So if we do this, check here. I'm going to use the exact, see what I talked about here? I'm going to use the exact same thing. Once you understand the models, once you understand the theory, the principles, same things apply. Nothing different, right? Watch here. Right, now I have to deal with factorization. The first thing that I have to do with factorization is what? HCF. If I look at this question here, 8x cubed plus 1, there's no HCF that I can take out between these two terms, right? So we bypass that step. So from here, I'm here. Now I'm at a fork. We have to make a decision now, right? Because we're going down the mind map. Do I have 4 terms, 3 terms, or 2 terms? I have 2 terms. And so I have to go like this. So under special binomials, check here. There's only 2 things that you could be given. It's either dots or it's sum or difference of cubes. So sum or difference of cubes. And so from these, I can see that it's sum or difference of cubes. That's the one that we're going to use. Right. Please, this one here is very rarely talked about. But this is going to link to something called cubic functions. You know, like how we're working with quadratic functions? Quadratic functions, this is going to lead to cubic functions. So you need to remember this. You'll need to remember the identity. So the way we do that is as follows. If I was given x cubed plus y cubed, you cube root the first term, you cube root the copy the sign, cube root the second term, square the first term, multiply both the terms, x times y, and change the sign. Minus. Sorry, square the. Wait, let me do this again. Sorry, my bad. So you cube root the first term, it gives you x. Write the plus sign, plus. Cube root the second term, y. Then you open the next bracket. Listen, you open the next bracket. Square the first term, x squared. Multiply both these terms together, x times y. Change the sign, minus. Right, minus, and then square the last term. Plus y squared. Right, if I add x cubed minus y cubed, it'll be cube root the first term, cube root the second term, copy the sign. Square the first term, x squared, change the sign, multiply both those terms together, and square the last term. Right. So we're going to do the exact same thing here. There's no HCF, so I have a sum of 2 cubes. So this is for the sum of 2 cubes. This is for the difference of 2 cubes. So we're going to work with this. These are what we call identities. Identities, which guess what? I mentioned it here. There's it here. It's the 4th type of mathematical statement. Right. Yeah, so these are called identities. So now we can just employ it. So cube root the first term, you get 2x. Copy the sign, cube root the second term, you get 1. Then we need to square the first term, it'll give you 4x squared. Multiply both the terms, it gives me 2x. Change the sign, minus. Square the last term, plus 1. And that's your answer. Now, you see when you're doing factorization gets very tricky because at the end here, let me check this out. The last step to factorization. So once you do this here, once you go through these parts, there's a last step that you need to do. And it goes as follows. So after you do all of this here, they all lead to the same point, is to distribute. So you distribute and you check if the answer is correct. So distribute and check. So what are we distributing? Remember I said factorization and products are reverses of each other. Factorization and then you have products. They are reverses of each other. And so if I go this direction, if I'm factorizing something, then to check factorization, I can use products. If I got products, to check products, I can use factorization. It's the exact same idea. So we have this here. I've factorized it in order for me to check it. See, I went down here. This is factorization. If I want to go back up, use products, right? If I was given this here, this is products. If I was given this here, this is products. So I'll distribute and I will get this answer here. But if I want to go back in the reverse direction, I'll do factorization. So let me do this here just to clarify. we given factorization, to go from year to year, we use factorization. If I want to check, I must distribute. So I have to go in the opposite direction, it'll be products. See, here, to go from year to year is what? Products. If I want to go back up in the reverse direction, I must use factorization. Can you see that? The inverses. So that's what I mean by distribute for factorization, because for factorization, the way we can verify our answer is through distribution, which is a rule for products. Okay. And so if you do that, you would obviously get this answer, right? I'm not going to do it, right? But you will get that answer there. So that's the distribution step. The last step is check. What are we checking for? Right? So remember, these are two distinct things that we're doing. We're distributing and then we're checking. We are checking that these are what we call factors, that each factors are in its simplest form. So this is in its simplest form and that is in its simplest form. And so this here, I'm sure you all would agree that this is in the simplest form, right? Because if I want to do that, how do I check if it's in the simplest form? Go back to the top. Can I take out an HCF from this bracket? No, I can't. Then we have to look at how many terms do we have? We have 2 terms in this bracket. Can we simplify it? Using dots? No, you can't. Sum of difference of cubes? No, you can't. So that's in the simplest form. If I look at this here, go back. So it's like a cycle. For the checking process, you come all the way back up here. Right, because we're checking. Let's look at this bracket here. Can I take it an HCF? No, I can't. How many terms do we have? We have 3 terms. So we have to employ trinomials. If you do this here, you will realize that we have that you can't factorize that. Right? I'm going to prove it on the calculator here. When I say that, I mean you can't find 2 numbers that are multiplied. We'll give you the middle term, and when you add it, we'll give you the last term. And so what we'll do is, if I check here, I'll put in 4, I'll put in -2, and I'll put in 1. You can see, it gives me imaginary. What does imaginary mean? It means that there is no x-intercept. It means the function does something like this here. Concave up, CA, concave up function. Can you see that? Doesn't cut the x-axis. So there's no way I can simplify that. Okay, now why am I saying this? Because this is what happens. You could be given this question here. X to the power 4 minus 16. Right? What do we need to do? First step, HCF. Did the HCF, how many terms do I have? I have 2. From those 2 terms, am I going to use dots or sum and difference of cubes? I'm going to use dots. Square root of the first term plus the square root of the second term, square root of the first term minus the square root of the second term. Then we need to distribute and check. So if I distribute, right, I do in fact get this here, right? If you distribute, you'll see it. Now we have to do the checking step. Let's look at this bracket. Can I take an HCF? No, we can't. There's 2 terms. Can I use difference of 2 squares or sum and difference of cubes? I can't use either. So that's in its simplest form. Okay, that's in its simplest form. Let's just keep it like that for now. Right? If I look at this one, we're in the checking step. Go back to the top. Can I take an HCF? No, I can't. How many terms are there? There's 2. Which of the 2 I'm going to use? I can use dots. Can you see that? Now, this is why this can further be simplified. And so the examiner, they're very sneaky because they use this word here. Factorize fully. To factorize fully means that every factor is in its simplest form. See, this, and this are infactorable. You can't factor it further. So that's when you know it's in its simplest form. And how do you know? You go back and you check. So to check if it's in the simplest form, you go back to the top and you employ the same approach for each bracket or each factor. Right, guys, I hope you're understanding. Is everyone understanding? Can you raise your hands or something? Is everyone understanding? Everyone's on the same page? Sumesh, we good? Okay, perfect. Okay. Raquel, are you understanding? Thumbs up or something?
Yeah, I'm understanding. Thank you so much. I'm so sorry. I don't know how to raise my hand on this thing.
Oh, no stress. Perfect. Delan, how's it going? All right, lovely. Okay, guys, right. So we got that part done now. Can you see? We literally covered so much and we're employing the exact same ideas. Rinse and repeat, rinse and repeat. We want to learn systems and not questions. All right, if I look at this one here now, if I look at this here, this is a trinomial, right? So it's 2x squared minus x minus 6. So we 2x squared. Oh no, this is here. Right, so look at this. See, 2x squared minus x minus 6. Now listen to this, right? Okay, we're doing factorization. We're still under the factorization topic. Can we take it in HCF? No, we can't take it in HCF. How many terms do we have? We have 3 terms, so we have to do trinomials. One of the most powerful techniques that you... Okay, just 1 minute. Sorry, guys. You guys, let's continue, right? Yeah, so as I was saying, one of the most powerful principles that you can use in literally any subject, right? And I know this firsthand because I use it quite frequently, is mind maps, right? And what mind maps do, they give you a bird's eye view of the topic. And so we've done factorization, right? On one day, our teacher did factoring by HCF. On another day, they did grouping. On another day, they did trinomials. On another day, they did dots. Some random day they did some indifference of cubes. What mind maps enable us to do is it enables us to see in the grand scheme of things, how do everything connect? Because if you can see that, or how does everything connect? Because if you can see that, then you can come down to powerful conclusions, right? You can come down to powerful conclusions, like how if there's the number of terms will dictate the approach that you use in maths. Now, while mind maps are important, there's a limitation with it. You can't put so much of information there that you make it cluttered, right? And so what we do is we zoom out. This is what we mean, or this is what I do when I use mind maps. I first zoom out. I want to write down all of the main headings that we've done, and I want to see, okay, in the grand scheme of things, how does everything fit? So I would have done this, 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 and then I've said, okay, wait, we started off with that, we went here, and then I can see, okay, there's a pattern here because the number of terms that we have, dictates the approach that we use, and then that's how we create this entire mind map. But then you can't only do that because then you basically too zoomed out. You don't understand how everything fits, and so to do that you have to zoom in. So you understand how everything fits, but you need to also understand each element of it. And so you zoom in and you focus on subcategories. And the reason I brought this up is for trinomials. When you have trinomials, you can have one of the 3 cases, right? You can have one of these 3 cases. So you can go and update this diagram. You could have something like this here. I'm going to list it out as examples. Cal, I'm not going to give formal terminology here because it's going to get a bit confusing. So you could have one of this. You could say, okay, x squared plus 5x plus 6. You could have minus x squared minus 5x plus 6. Or you could have something like 2x squared minus x minus 6. And so if you look at this here, okay, let me just say it. If you look at this here, what's different? The coefficient in front of the x squared term. And so these are the 3 cases that you must remember. If the coefficient is 1, you employ one technique. If the coefficient is negative, you employ another technique. And if the coefficient is bigger than 1 or some number other than 1, so let me write here, other than 1, then you employ another technique. Very important stuff. Extremely important stuff. Okay? I'm going to do all of these examples and I'll tell you why I did that. Right. And so if I do this here now, what technique do we employ here? We do the following. You multiply the coefficient of the x squared term to the constant term. If I do that, I get minus 12. Then you list out the factors of minus 12. It'll be 1 times 12, 2 times 6, and 3 times 4. Then I ask myself, the product of what 2 terms will give me this term, right, which we've already figured out. So the product of these terms here will give me 12, right? But the sum of which of these pairs will give you the middle term. And so if you do that, you'll see that it'll give you 2x squared, see, plus 4x minus 3x, gives you the middle term, but when you multiply this together, it gives you minus 12. Don't forget the sign, minus 6. Right. I don't want to go into too much depth, right? But this is basically the basic idea. I want to find out, multiply the first term to the last term, gives me minus 12. Then I want to find out the factors of minus 12. There's it here. because these pairs must multiply to give you minus 12, right? And then I want to find out from these pairs what, when added together or subtracted from each other, will give you the middle term. And we found out it's this here. Okay. And now we can factorize. This is only when you do the factorization. So again, we're only doing it when the term in front is some number other than 1. Okay. And so if I want to factorize this, how many terms do we have in this expression? We have 4 terms. And if we have 4 terms going back to this diagram here, we have to use factoring by grouping. All right, so you're obviously supposed to start here. There's no HCF, so then we can go straight to grouping. And the way we'll do that for grouping, the first 2 terms go together and the second 2 terms go together. Right? That's the simplest way we can remember it. And then, then let's do HCF here, HCF here. Let's see what we get. If I do that, the HCF between the first 2 terms is 2x into x plus 2. Distribute it and see if it's correct. Say 2x times x is x squared, 2x times 2 is 4x. Yeah, the HCF here will be minus 3 into. Minus 3 times what number will give you? Minus 3x. X. See, minus times a plus gives you a minus. 3 times 1 gives you 3. And 1 times x gives you x. Right, again, we're using S and V. Minus times a what will give you a minus? A plus. 3 times what will give you 6? 2. Right. And then we can pull out what we call the common binomial factor, because this binomial is common to both these terms. See, the minus sign separates these terms. It's a common binomial factor. So this here and this here, I can pull it out of the bracket. If you can visualize the bracket that I'm talking about. And so it'll be x plus 2 is outside the bracket. This will be multiplied by what? 2x. And this will be multiplied by what? Minus 3. And then we factorize that, right? And yet again, after you do all of the factorization, come back down, distribute. If I distribute that, I do indeed get this here. Remember, everything comes from the question. You don't worry about all of these intermediary steps. You go back here. You check, if I distribute, do I get this? The question is what matters, not your simplification steps. This is what matters, right? And so when you distribute, check if you're getting this. That's what the examiner is testing, right? So don't distribute and check, oh, do I get that there? No, you don't. You go back to the top, right? Distribute, I get that. Check. I look at this here. Can I take it in HCF? No, I can't. There's 2 terms. There's only 2 ways I could do it. Dots are sum and difference of cubes. That's not going to work. Same thing here, same story. But so that's so that's everything there for factorization. Now, if we do this one here, right? This is why I do this here, because we do. In fact, you see, this approach here you can use. There's no calculator, so if you want to use a calculator, you can put it in here, and you'll get 2 minus 1 and minus 6, right? And then you get here x is equal to 2, and then you'll get x is equal to minus 3 over 2. X is equal to minus 3 over 2. And so the way you'll do this now is you'll say, okay, x minus 2 is equal to 0, and here you'll say 2x plus 3 is equal to 0. And these are your factors. These are your factors that will make up this one. Can you see that? But you can see the approach now. When you don't use a calculator, you can see how you can do that. Now you see why this is so important. Why I don't like using a calculator is because of this question. When you have a negative number in front of the x squared term, you have to factor it out first. So it'll be minus into x squared plus 5x plus 6. Okay? And then you put this into the calculator, you can solve it mentally. This will be x plus 2x plus 3, right? This is the answer when you don't use a calculator. But if you do use a calculator, see what's going to happen. Put minus 1 for x squared, minus 5, and then minus 6. I'll get x is equal to minus 2, x is equal to minus 2, and you'll get x is equal to minus 3. Right. And if I do this, take it across, it becomes x plus 2 is equal to 0, or x plus 3 is equal to 0. Can you see that? Only one half of it. The minus sign, you didn't include it. Right? So that's the reason why when you have a negative, you must factor out the negative. Then whatever's in brackets, that you can put into the calculator and solve. Right, so can you see here now? That's basically the instances where you need to be very careful with when working. Right? What are these? What are these? These are the same as the x-intercepts of the parabolic function. If you can see it, it's the x-intercepts of the parabolic function. We're using the zero factor property, and we're finding the factors that make up this expression. Same thing, nothing different. But the only thing you need to remember here is this minus sign. Okay, because if this was an equation, we would have done this here. Minus x squared minus 5x minus 6 is equal to 0. Same difference. We're treating this here as an expression. What is an equation? An equation is a collection of expressions. There's an expression here, there's an expression here. So whatever you're doing to this expression, you'll employ the exact same thing here. You're isolating this part. Right? So if you look at the calculator carefully, let me just go back here. Let me show you. Can you see that? Ax squared plus bx plus c is equal to 0. Equal to 0. Can you see that? It's equal to 0, which is an equation. You have a left-hand side and a right-hand side. This is indirectly making use of the zero factor property. So this is equal to 0 or that has to equal to 0. See, this has to equal to 0 or that has to equal to 0. Same thing, nothing different. Okay. So yeah, so we got that part done. And then the last one here, if you look at this, a squared minus 2ab. So it's a squared minus 2ab minus 2b squared. It's ab. Yeah, if you solve this here, again, I can't take out an HCF. So I have to go to, there's 4 terms, yes, I have to use factoring by grouping, work with the first 2 terms, work with the second 2 terms. So I'll have a into a minus 2b, right? And here I'll have minus b into 2b minus a. Right, so it'll be a times a is a squared, a times minus 2b will give you minus 2ab, minus b times 2b will give you minus 2b squared, minus times a minus is a plus, b times a is ab. So this is perfect. But now what you would notice is that these binomial factors are not the same. So we can't factor it out. But what we can do when you have a negative in between terms, this is called the change of sign rule. You can swap the terms in the brackets, but factor out a negative. So it's only when the term, there's a minus on at least one of the terms, right? That's only when there's a minus on at least one of the terms. If there's a plus, you can't do that. You can't swap and then pull out a negative, right? So how would you do this? See, 2b minus a is the same as minus a minus 2b. If you distribute here, you will see you do getting the same answer. And so what we can say is, wherever I see this, I can input that. So I see it here, I can take this whole thing and put it in there, see what will happen. It'll be a into a minus 2b, the minus b, I saw this here, I'm going to put that in, multiplied by minus a minus 2b. And so if we do this, it'll be a into a minus 2b minus times a minus is a plus, b into a minus 2b. And therefore, if you simplify, it'll give you a plus b into a minus 2b. Can you see that? And yeah, because now we can take it out because there's a common binomial factor. And so what we can say is, if you're doing factoring by grouping, and the common binomial, the common binomial, there's no common binomial factor, then one of 2 things could happen, right? One of 2 things could happen. It's either you got this part wrong, means you didn't do the factorization correct, or the second thing is the change of sign rule. Let me write it here. Change of sign rule. Okay, guys, a change of sign rule, right? But when can you use this? If one of the terms has a minus sign. It's good knowing these things, but you also need to know what, when, why, and how. When can I employ this? When at least one of the terms has the minus sign. Then you can employ it. If it has a plus, let me prove it to you. If it has a plus b, I can't just go do this. I can't say it's the same as minus b plus a. Can you see that? Because what it gives you, minus b minus a. Not the same. Not the same. So that's why we can't. At least one of the terms must have a negative. Okay. So yeah. So I think Yeah. Okay. Okay, guys, yeah. So now you can see we've done this part, right? So we've done practically most of the expressions part, right? There's it here. We've done most of the expressions, we've done products, we've done factorization, we've done rational expressions, we've done exponential expressions. So now we can move on to equations. Like I said again, all of these ideas, even linear equalities, all of this here will all basically lead up to functions. If you understand this, then you understand functions. If you understand functions, then you understand this. Same thing. All right, so now let's go to equations. When you're working for an equation, you're not simplifying anymore. Now you are solving. So we need to solve for some specific variable. Okay. So yeah, let's do that. And remember, there's the three categories here: linear, quadratic, and exponential. Right. And then you just need to know, like, how do you identify a linear? You'll just see x in the equation. There won't be, or x will be the um a term in the equation. For quadratic, you'll see an x squared, and for exponential, you'll see that the variable is the exponent, right? So here the exponent on x is 1. Here the exponent on x is 2. Here the exponent is the variable, or x is the exponent. I hope you understand. That's how you identify. So when, there's it here. That's how I wrote it here, when. And then we'll figure out the how now. Okay, so let's go back to these questions. Where is it? Right, there's it here. I'm dealing with an exponential. No, sorry. So we got x squared equals to 5x. So now what do we have here? We have a quadratic equation. How do you solve a quadratic equation? Come back up here to spine map. How do you solve it? Either using factorization or use substitution. So if I use factorization, then what do I need to remember? I need to remember my factorization rules. Right. So if you do that, how do we do this? Right, when you're using factorization, the first thing you need to make sure is that the right-hand side is equal to 0, because when the right-hand side is equal to 0, then we can make use of the zero factor property. From a function standpoint, this is actually the x-intercepts of the function. X-intercepts. And so if I do that, I'll have x squared minus 5x is equal to 0. So the right-hand side is 0. Done. Then we can do factorization. If I do factorization on this, what's the first rule? I need to take out an HCF. The HCF between those two is x into x minus 5 equal to 0. Now, since we have this factorized fully, listen to that, factorized fully, then I can use the zero factor property. If a multiplied by b is equal to 0, then, then a is equal to 0 or b is equal to 0. So this is a is equal to 0 or this is the same as b. X minus 5 equal to 0. And so if we simplify, x is equal to 0 or x is equal to 5. So what I can say is that the x-intercepts of this parabola is x equal to 0 and x equal to 5. And so if you're going to sketch it, this is you'll only be able to do this when you get to grade 11, right? But if you want to do it, I know one x-intercept is here, another one is here, isn't it? At somewhere at 5. And then the a, you see ax squared plus q. A is positive, so it's a concave up function. The function will do something like this. Can you see that? Start thinking like this. Okay. Yeah, if you want, you can put this on Desmos and you'll see it'll give you the exact same thing. R is equal to 2 square root of x over 3. So R is equal to 2 square root of x over 3. Yeah, so now can you see here? What are we doing? We're trying to solve for x, but we have unknowns. And so if we have unknowns, what we're saying is make x the subject of the formula, which leads to the topic of literal equations. I have explained why this is so important, but for now, let's just solve for this. And so if we do this now, remember we're solving for equations. So when you're doing like literal equations or any equation for that matter, we're still going to use a BODMAS. That's like the primary rule that governs all of this, but we're doing it in reverse. There's no subtraction, there's no addition. we can use multiplication and division now because we're trying to isolate the x. We're trying to make x the subject of the formula. And so if I do that, I'll have r multiplied by 3s is equal to 2 square root of x, right? Let's swap it, right, to make it a bit, I like the x's on the left-hand side, right, is equal to r multiplied by 3s. Then you can see multiplication here, I'm trying to isolate the x. What do I need to do? Divide by 2 on both sides. If I do that, then I'll have the square root of x is equal to r be s here, rs or 3rs over 2. Just keep your numbers one side, variables on another. That's just a matter of format, right? And then now what do we have here? We have exponents. How do you get rid of a square root? You square both sides. So if I square both sides, I'm left with x is equal to 3rs over 2 all squared. And if I do that, then we'll have to 9r squared s squared over 4. Done. Simplified. Right, but I go into much more depth in the videos, Raquel, about literal equations. There's certain things that you need to keep in mind when solving these questions. Okay, like if I just have to give you an example from the top of my head, it'll be like x plus y plus 2x is equal to 10, let's say. And if I say solve for x here, then when you remember again, I can see a plus sign